On this week's topic of climate change, this lecture is about climate impacts, both in terms of what we've already been observing as a result of the rise in greenhouse gases and what we can expect given different projections for greenhouse gas level rises. So, for some context, the last time the Earth had a carbon dioxide level similar to today's in the atmosphere, it was on average about 3 degrees Celsius warmer. 3 degrees doesn't seem a lot. It's the difference between, a warm part and a cold part of a day. But the world then was dramatically different. Greenland's hills were green, part of Antarctica was fringed with forest, and the water that is now frozen over these landscapes of Greenland and Antarctica, which has now formed kilometers of ice, were then part of the oceans. And that meant that sea levels were 20 meters higher than today's sea levels. And the International Panel on Climate Change, IPCC, they estimate that the mean surface temperature is now about 1 degrees Celsius above what it was in the pre-industrial world and rising by about 0.2 degrees Celsius a decade. And there are natural variations in the Earth's temperature. But climate models using state-of-the-art statistical techniques can hindcast what the 20th century would have looked like with natural forces only, taking into account the oscillations of the sun and different variations in natural cycles like El Nino. And the observed temperatures here, as you see on the dark line, these are temperature observations since 1900, and those can only be explained when you include natural and human forces. So it's very unlikely that the observed temperature rise that we have seen since this date would be caused by natural forces only. So these in these scenarios in blue here are climate models that don't take into account any human factors being anthropogenic greenhouse gas rises. So we can say that natural variations in the Earth's cycle and in the climate cannot produce decadal warming on this scale. And that's why we say global warming is unequivocal. There is no real doubt that global warming is happening and that it's caused by humans. So here is the global temperature change in 2018 and its deviation from the average in between 1950 and 1980. You can see that there has been warming almost everywhere. These blue areas, there's been some slight cooling. And it's warming to a different degree in different locations. So in mid to high northern latitudes and in some other places, there has already been warming of 1.5 degrees or more. And much of the Arctic has seen 3 degrees Celsius. And as a result, we can see some dramatic changes in the Arctic's climate. We've seen very dramatic burning in Siberia of peat land and forestry, which has released masses of carbon. Furthermore, different parts of the world respond in different ways to the rise in temperature and into the concentration from greenhouse gases rise. For example, ocean temperatures increase more slowly than land temperatures because of the different heat capacity of air and of water, and then also because oceans lose more heat by evaporation and they have a large heat capacity. Also, high latitude regions, either far north or far south of the equator, warm faster than the global average because of this positive feedback. So there's a little bit of warming, ice is lost. That ice had been a deflector of energy, and when the ice is gone, then it heats up faster. So these positive feedbacks from the retreat of ice or snow cause high latitude regions and also mountainous areas to heat faster. And that's why we're seeing an accelerated decrease in glacier area. That means that there's an increased transfer of heat from the tropics to the poles in this warmer world, and that enhances warming as well. As a result of that reason, that fact, Arctic sea ice is at a record minimum for the date again. If you want to follow this in almost real time, I recommend you follow Zach Lab on Twitter. He posts these statistics almost every day or every week, and we can see that this is the Arctic sea ice for the current date, just a day or two ago in October 2020, and it's at a record minimum for the date. So if you can see here, since the 1980s in the purple, the extent in terms of millions of square kilometers of Arctic sea ice has gone from about 8 to 9 million square kilometers to only 4. So actually, for the date, we're at half the amount of sea ice that there was in the 1980s. That is very stark change. What we're seeing also as well is an acceleration in the loss of sea ice in Greenland, and I share with you this film called Chasing Ice, which I recommend, and I skip forward these videographers recorded the largest ever loss in ice from Greenland, with these glaciers carving off here. It's really remarkable footage, and I recommend it. It's interesting that Greenland's name, it's a misnomer, so Greenland is anything but green. It's the result of actually a clever marketing campaign from Eric the Red, who wanted to attract Viking settlers to this icy place. So he didn't know that Greenland had been covered in lush forests many millennia before. And many decades afterwards, the vast ice sheet is in fast retreat. The ice on Greenland holds enough water to raise global sea levels by more than 7 meters if it all melts and goes into the ocean. For this reason, climate scientists closely monitor the levels of ice in Greenland and monitor the seasonal trends and how quickly it starts to melt in the spring and how much it melts into the autumn. Some recent study in September-October 2020 found that the Greenland ice sheet is losing mass at really accelerated and unprecedented levels in the 21st century, making it the largest contributor to rising sea levels. And one very stark finding is that actually annual snowfall in Greenland can no longer replenish the melted ice that flows into the ocean from the glaciers. That's this new conclusion from this analysis, which observes satellite data from around 40 years. So they think that the ice loss now has triggered an irreversible feedback loop. So there's such an amount of ice and water flowing off Greenland that the sheets will keep melting even if we reduce all greenhouse gases to zero very, very quickly. So that's very bad news for coastal cities, and it means that we should really be paying attention to what we call climate adaptation as well as mitigation, because of the lag between action and effect in the climate. So since 2000, this study estimates that melting ice has contributed about 1 millimeter a year to rising sea levels. And as I said, the loss of the entire ice sheet would contribute to 7 meters of sea level rise. People listening from Cork might want to consider where they live. Here's some data from The Economist, a recent chart based on that paper. And you can see here that the cumulative melt from Greenland's ice sheet, that's the net mass balance, in gigatons, that's billions of tons, is cumulatively nearly 5 billion. So nearly 5 billion tons of water have been melted from Greenland, and this is the net annual discharge, and we're reaching almost 2 million tons a year, and that accounts for that. So that's the net discharge that accounts for the snowfall as well. So that's very, very stark. This then gives you projections for the mean sea level rise. So it shows that the mean sea rise has risen by a number of millimeters since pre-industrial levels. So we had tide gauge data until the late 20th century, and then we have satellite data to very accurately measure the rise in sea levels. So as a result, we can see cities like Venice suffering an awful lot. And these are different climate scenarios depending on how quickly we mitigate or not, with this red being the sort of worst case, that we burn lots of coal, which is very unlikely. So the sort of now current projected range of sea level rise in this century up to 2100 is between 30 to 120 centimeters, depending on sensitivity and things like that. So there's quite a high range of uncertainty, but we know for certain that rise is happening and it will continue to happen. There's also the possibility that if there's an increased melt from the Antarctic ice sheet, up to 2.4 meters of total rise by 2100 is possible. And this gives you an idea about where the cities are at different levels of rise. So you can see here we've had about 20 centimeters of sea level rise since pre-industrial times, and as a result, the city of Venice is experiencing frequent flooding. Next, let's say if all other ice the next is by 2100, we're likely to see the worst case scenario of maybe 1 meter to 1.2 meters, or maybe a bit more if Antarctic is included. And these cities, San Francisco, Lower Manhattan, LA, St. Petersburg, Hamburg, Amsterdam, they're all going to be experiencing much more frequent flooding, many people suffering there. If we're looking out a few centuries, 800 years, 8,000 years, we're looking at all major cities and the coastline of the world basically being completely reconfigured as a result of humans' greenhouse gas emissions. So we have dramatically been altering the climate system and weather change as a result of that. And just a summary of these effects, it's obviously not just sea level rise, all Earth systems are impacted by that. And you can see this, a summary from NASA here for a summary of all these things. So first of all, global warming is also warming the oceans. The ocean has absorbed much of the increase in warming that has happened, that about 1 degree Celsius warming since the late 19th century. And I should note as well that the majority of that 1 degrees of warming has happened in the past 40 years. The 6 warmest years on record took place since 2014. So we're warming every year. The September 2020 was the hottest September on record. The second hottest September on record was in 2019. And many other months have been setting records in terms of heat as well. So as I said, the ocean has absorbed much of that increased heat, and the Earth stores around 90% of that extra energy that it's getting as a result of greenhouse gas level rise in the ocean. Warming the ocean then has consequences, obviously, for sea ice. I showed you the pictures of the Arctic. It's also causing glaciers to retreat, glaciers which are essential freshwater supplies and supplies of rivers in many parts of the world, and they're retreating almost everywhere: the Alps, Himalayas, the Andes, the Rockies, Alaska, and Africa. And billions of people depend on those glaciers for their drinking water. Also, the number of record high temperature events across the world has been increasing. The number of record low temperature events has been decreasing as well since 1950. So we've seen intense rainfall events, more intense hurricanes as well, which have been attributed to climate change, and also changing patterns in rainfall and drought. So drought seasons are getting longer, rainfall is getting more intense, which affects crop yields and mudslides and things like that. Obviously, sea levels have been rising. So global sea levels rose about 20 centimeters in the last century, and the rate in the last 2 decades has been accelerating again. It's every year the global sea level rise is accelerating. We're at the start of this curve, which is bending up very, very quickly. As a result of the heating and the changing weather patterns, more extreme weather events are happening, and they're happening more frequently and more intensity. For example, weather events like the drought in California has contributed to around 4 million acres of forest burned this year. You've seen the pictures of that on the news, with people not able to leave their houses and and air quality getting very significantly worse, people dying. Also very significantly, as a sort of a positive feedback loop, there have been wildfires blazing in the Arctic Circle this summer. This summer had extreme wildfires blazing in the Arctic Circle. Last year was another record for that. That incinerated tundra. Tundra is very much made up of peat, which is a carbon source. It's a carbon sink. So, you could, if forests burn, they can regenerate in maybe 100 years. So there's sort of a no net carbon loss as long as the forest is allowed to regenerate. But peat doesn't regenerate as fast as that. Peat grows over tens of millennia. So the carbon is permanently lost to the atmosphere. So around 200 million tons of carbon dioxide has been released to the atmosphere as a result of the forest fires. And also a lot of the peat in the Arctic Circle had been under ice, and as the sort of the ice is melting, the peat is drying and burning. It's very, very significant. Ecosystems, plants, animals rely on different weather systems for their survival, and ecosystems are changing faster than many plants can affect. So the climate crisis is also causing a crisis in biodiversity, and many species of plant and animal are becoming extinct at unprecedented rates. And finally, oceans are acidifying. Oceans have acidified again because of additional carbon dioxide, which is dissolving into the oceans. So an extra carbon dioxide in the atmosphere gets dissolved into the oceans. The oceans become more acidic, and this causes huge problems for creatures with exoskeletons, like shellfish and like coral reefs. So this is the reason why we see huge die-off in coral reefs all across the world. So if you want to see the Great Barrier Reef, I'd go sooner rather than later. There's also no well-defined or well-understood tipping point. People sometimes think that, we've gone past the point of no return, or there's some sort of like magic year in 2030 by which we have to take some action. The cumulative impact of past carbon dioxide emissions already have a huge impact that will have an effect for centuries to come. But the more greenhouse gases that we emit, the more warm and more intense effects there will be. Basically, a lot of these effects are just related to the concentration of CO2. So the faster we reduce CO2 emissions, the more we can reverse this. And finally, further warming is absolutely certain because there's an inertia and time lag between heating and emissions. Because of the long life of carbon dioxide, which is the long-lived greenhouse gas, which is most significant. And this gives you an idea. This is from the first IPCC report to show this difference in the inertia between different response timeframes. So as I said, at present, further warming is absolutely certain. Whatever the world does about its emissions, obviously, the more that we emit now, the worse the effects will be in the future. You can kind of compare this to like a pan of water on the hob, which takes time to boil when the gas below is lit. So the world's temperature is taking time to respond to the heating imposed by the concentration of greenhouse gases. But just even if you turn the heat off that pot of boiling water, it's not going to cool down immediately. That's going to take a long time to cool down. So, for example, if we peaked CO2 emissions immediately, so if this is CO2 emissions and it goes to zero, this is what will happen to CO2 levels in the atmosphere. They'll stabilize. So CO2 only stabilizes as a concentration in the atmosphere when absolute emissions go to zero, because it's just like, it's not, you're emitting it and it stays concentrated in the atmosphere. Temperature then will keep rising for a few centuries beyond CO2 stabilizes in the atmosphere. And sea level rise due to thermal expansion will take a lot longer to stabilize, centuries to millennia, because it takes time for this warming to translate into thermal expansion from sea level rise, but a sea level rise due to ice melting will take several millennia, again because it's not like you can put that ice back on Greenland, or you can't put that ice back on Antarctica if we got the temperature down again. It's a non-linear thing. You melt it, and it takes a lot more cooling to freeze it again. One interesting policy implication of this inertia is that it's very difficult to see the immediate impact of our policies and actions. It's much easier to make a policy when you can take an action and then immediately you see the consequence in terms of less sea level rise or so on. But the policy kind of options that we make now will have impacts in many generations to come, which is why it's very, very hard to bring those policies about, and it has been. This shows the climate warming in 2100 according to different pathways. This is different RCPs. RCPs are representative concentration pathways of future emission scenarios. Here is something like 1.8 degrees of global warming. That would be something like in line of the Paris Agreement. And then these two RCP 2.6 and 4.5, they're somewhere in the middle, and then this is the more extreme RCP, and obviously the darker the red, the more warming there will be, and you can see that there is certainly warming everywhere. So in the past there has been some mostly warming and some cooling as a result of greenhouse gas emissions concentrations. In the future, these models show only warming, and warming to different degrees everywhere, but more warming in the Arctic and at higher latitudes, which is certain. And you can see as well the impact of that on people if you map the warming against where there are actually people. In the current day, less than 80% of people have experienced warming of less than 1.5 degrees, and less than 20% have experienced warming of over 1.5 degrees. But even in the best case scenario here, the 1.7 degree Celsius of average warming, that's RCP 2.6, around 20% of people will experience warming of over 2 degrees. And if you go up here, RCP 8.5 is seen as an unrealistic sort of disaster scenario. But by 2100, let's say in the two worst case scenarios, pretty much everyone in the world experiences warming of over 2 degrees Celsius. And many of you watching will be Irish living in Ireland, and you won't you'll say how bad, but this has really severe consequences for the livelihoods and the lifestyle of people all across the world. Global warming also has very important implications for precipitation, and it's expected to result in dry areas becoming drier and wet areas becoming wetter, especially in mid and high latitude areas. And this is a good link if you're interested in what future rainfall will look like. The Mediterranean region in this model is expected to have around 20% less precipitation in 2100 in this scenario. And many areas in Africa, Australia, Chile, and North America are expected to become 10% drier. An interesting thing is that these changes tend to increase proportionally with warming. So double the warming implies double the sort of change in wetness and cold and dryness. So I think that's been a bit of a stark lecture. I hope it hasn't been too pessimistic for you. And I hope you also feel like there's plenty that we can do to mitigate this, and that we need to mitigate this. We have the tools, and the rest of this module is somehow how to achieve those tools in terms of policy, in terms of technology, economics, and that everybody can play a part in how we mitigate this as best as possible.